Hello, in today's group meeting, we have Richard Lopp. This is the second lecture on the light and atoms, the multipolar Hamiltonian quantum delocalization. This is a series of lectures that Richard is given on understanding the light-matter interaction. Richard, whenever you want, please, floor is yours.
Thank you. Okay, so as you said, it's going to be the second rendition of light and atoms. So if you want seminar or lecture, and today will be all about some specific form of the light-matter interaction, a specific model that is ubiquitously used in quantum optics and also in RQI, relativistic quantum information, and so for its dominance in many applications. I want to discuss this in very much detail. So first of all, today is going to be we start with a slight recap just to know what we did last week. And then we're going to start really working with the usual approach, which is what I call the effective approach. And once we covered that and cleared that, we are ready to go to discuss the fully quantum multipolar Hamiltonian version. And in the end, we are just going to wrap up. Okay. So what did we do last time? So we derived the minimal coupling Hamiltonian after we saw that we can decompose in the non-relativistic approximation the field components into longitudinal and transverse components. We then quantized the minimal coupling Hamiltonian in the Coulomb gauge, and this was a really very simple prescription that allowed a very simple quantization procedure. And in the end, we showed that we can compare different representations and connect them by unitary transformations. And we also saw that not all of these are equivalent to a change in the Lagrangian. What we also discussed that not all of them can be actually connected by unitary transformation, and this will relate then to the next week. And then finally, we saw that gauge transformation are a special subset of those. Okay, so what we're going to do today in particular is we're going to derive the multipolar Hamiltonian. And there are a couple of questions in particular that we want to answer. So what are the assumptions for deriving the specific model? And this will relate to the center of mass, it will relate to gauge degrees of freedom, and it will be concerned with the motion of atoms. And then once we know this, we can ask the question, so what are the dynamics that we are therefore neglecting? And this will be related to what is known as the Röntgen term or Röntgen terms associated with different degrees of freedom and also with center of mass delocalization. Okay, and in particular today, I will follow mostly these two papers here. And one is by Kobe and Gray, and the other is with my supervisor, Eduardo Martinez, and then myself. Okay. So let's start with the effective approach. So what I mean here is, let us consider the most simple setup of a bound atomic system, a hydrogen atom. And we assume now we have a non-relativistic electron that is bound in a Coulomb potential. And this potential in turn is generated by a classical proton of an infinite mass if you compare it to the electronic mass. And then in a similar spirit as we did last week, one can easily derive the minimal coupling Hamiltonian. Now here we are not assuming a particular gauge, so we can choose the Coulomb gauge, but in this form here, we didn't choose anything so far. And so this is just a one particle minimal coupling Hamiltonian. This is what I mean by effective, that in the end, even though we in principle, we are considering a two particle system, we are only really considering one quantum degree of freedom associated with the electron. So now what we also saw last time, and I'm going to repeat that here again, is if we want to consider a classical gauge transformation that is generated by a scalar function chi, in a classical case, we can easily substitute our scalar and vector potential of the usual form that we are all aware of from classical electromagnetism. But in the quantum case, if we have a unitary transformation that is generated by the generator capital lambda, this does not hold in general. And to see precisely what the quantum analogy is, let us define in covariant form the 4 vector potential, the 4 momentum, where we sort the scalar and the vector potential in there, and also the similar construction for momentum. Now, if you want to talk about observables, then we need to talk about gauge invariance of those observables. And let us assume we have an operator that is in principle a function of the 4 momentum and the 4 vector potential. Then if this corresponds to an observable, then we must have the condition of a gauge invariant expectation value in the following form. So the expectation value of the operator with respect to certain state psi must be the same as the operator in the new representation with the new state psi tilde psi prime. From this requirement, one can then relate these 2 operators via use of a unitary transformation. And one can also show then consequently that an operator that depends on the 4 momentum and 4 potential must be a sum of both. So what does it mean? So let us look at a couple of examples. First of all, so if you look at the 4 momentum, which corresponds to the scalar and the vector potential, we see it no longer transforms like in the classical case. In particular, we have the unitary conjugation of the operator, and then also some term that is particularly this quantum version term comes from the quantum. And what we see here, of course, now that it doesn't transform as we would have want for an observable. So this cannot correspond to an observable here. If you look now at the mechanical momentum, so at the linear momentum plus the E times the vector potential, then it transforms exactly in the form as we would like to. And we know that this can be used to construct an observable. Now, in principle, one can also construct the zeroth component of the mechanical momentum, which corresponds to the zeroth momentum of the 4 momentum and the scalar potential. And this also transforms in the correct way. However, this is not a Hermitian operator and therefore cannot be used as our observable here. And one can see that if you go to positional representation, the zeroth component of which corresponds then to the time derivative is not Hermitian. Okay, so what we know now is if we want to construct an observable, we can only have dependence on mechanical momentum and position operator. And so, as we saw also last time, one can construct, for instance, the energy operator of the kinetic energy associated with the mechanical momentum plus some potential energy. And as we also saw, this corresponds exactly to the Hamiltonian in the Coulomb gauge for the minimal coupling Hamiltonian. And this transforms exactly as you want to for an observable. All right. So now that we discussed this again, let's go back to our problem. So we started with a 1 particle minimal coupling Hamiltonian and associated with the electron and the Coulomb potential generated by the classical proton. Now we can consider a canonical transformation, a unitary transformation that is generated by capital lambda. And one can show then that this corresponds exactly to a gauge transformation. And from what we saw in the last, from this slide, we know how to transform the potentials. And the nice thing now here is that they can be expressed in terms of the electric and magnetic field. And this is something very nice because we don't have any explicit gauge dependence anymore in this new gauge. So we can rewrite our minimal coupling Hamiltonian in this new gauge. So here we have now the term that used to be P plus EA. And here we have what used to be the scalar potential. So now what are the terms and what are we usually considering? So let's say we want to do a multipolar expansion. So that means we want to have multiples of the electric and magnetic field operators. And this we can do also in terms of small parameters, that is the coupling constant E, and the localization of the atomic wave function, which gives us, in this case, the localization of the interaction. And so if we compare, we can neglect this E squared term. And what is this delta? So this delta is a self-interaction which comes from Coulombic self-energies, and therefore in principle needs to be regularized and corresponds then to a lamp shift. But to leading order, we will be able to neglect this. The other thing we will be able to neglect to leading order is the quadratic form of this, since it also will be quadratic in E squared, in E. And then we can also neglect the cross term of P times this term, because this will correspond to the magnetic dipole, and this will be also of subleading order. And so to leading order, only the usual electric term survives, but this is again in non-local integral form, and so we also want to have a multipolar expansion here. And so we can approximate this to leading order in this form. And this is the only surviving interaction between atom and field, and is what is known then as the electric dipole interaction. So this is the usual dipole interaction, but not quite the right dipole interaction. The usual form, as might be more familiar to quantum opticians, is a different form. So let us assume now something more before we derive this, this new gauge Hamiltonian. So we start out already with this approximated form. So we assume, since in the long wavelength approximation, that means the wavelength of all the field momenta is much longer than the atomic size, and therefore approximately the localization of the electron is at the center of the atom, and therefore the center of the atom was at 0. That is where our proton resides, and therefore we can approximate the field to be evaluated at the center of mass of the atom. And then we can derive this new Hamiltonian after a simplified gauge transformation, and this is what is usually done in quantum optics. So the electric field is not a function of the electronic position operator, but evaluated at 0, where the center of mass is. Now, the difference between these two models is of order of nabla E times two electric field electronic position operators, and one can show that in the position representation, this is exactly suppressed by a factor of the Bohr radius with respect to this interaction term. We will see later exactly how the Bohr radius comes in, but let's assume this is fine for now. And we see that this is a finite difference if we have a cutoff in the field momenta. Of course, a cutoff is essentially needed if we work with our non-relativistic prescription of the atom, since again, if we go to too high of momentum, which corresponds to Compton wavelength or the rest energy of the particles in consideration, we will get correction that come either from vacuum polarization or we get a particle creation. And therefore, in the end, a cutoff is always needed. But in this quantum optics form, of course, it is more explicitly needed. In the form that we had before, so evaluate at this position operator, we don't explicitly need to introduce a cutoff, since the localization is automatically bounded. And we will see that in one of the next slides. Okay, so let's talk a little bit more about this.
Richard, can I ask a question?
Yeah.
So the quantum optics one, right?
Mm-hmm.
Is this the only advantage that you don't put an explicit cutoff?
I mean, it's also simpler, right? Because in the end, you don't have to take into account where your electron is in the end.
Yeah. So it's a little bit like they are doing partial approximation instead of like keeping everything as far as they can and then drop stuff later, right? Mm-hmm. So so I was just wondering whether this is just a matter of like a convenience rather than say something disastrous can happen in some even non-relativistic region. Like for example, if let's say they were to do something similar to say a proton, and let's say imagine that you have this imaginary electron that has mass about the same as a proton, right? Then what will happen?
Well, so if we go here to position representation and we insert the energy eigenfunctions of the atom, of the particle, of the bound system, right? Then we will get the wave function associated with that system. And in general, that will be localized with some rather small parameter. And here in this case, it's the usual Bohr radius. And in this sense, you can say, okay, this to the lead, since we're only considering the leading order interaction, all the higher terms that was the magnetic multipoles and so forth are neglected too. So the difference between these models is also to a higher order.
So there's a couple of things though. The way you presented it, there's one thing you're not mentioning, right? That is how people have been used to it in the past and why it's wrong. The problem with 15 and 16, they clearly cannot be the same thing, right? Not even approximately, because 15 is a gauge-dependent thing, whereas 16 is not. So there's something here, there's some gauge that has been fixed or something, right? You would say. And then the problem comes when you want to use the wave function, when you want to compute transitions between different levels in the atom. If you want to compute your hydrogen atom and you want to compute the transition between 1s and 2p, then typically people take that dipole model and put, you know, the 1s and 2p on both sides. And then in the 70s, some people realized, people like Lamb, right, and others, Scully and others, what? No, if you do the calculation with the 15 one and the 16 one, you don't get the same results. How come? Well, you see, to get the Schrödinger wave functions that we see in textbooks for the hydrogen atom, the assumption there is that there is no current. So basically there's no way. The assumption is we are solving the wave functions themselves, as Richard even showed in the previous slide, right? The wave functions are gauge dependent. So because the wave function and gauge dependence, you need to actually use the wave function, the solutions to the Schrödinger equation in the same gauge as you.
No, Eduardo, I'm asking something simpler. What you're saying is very far-fetched. So.
Well, no, it's not. I think it's important. You cannot use 16. You cannot use 16 as an approximation of 15, and also it's kind of written like that.
I mean, it's so. Let me be clear how we get from here to here. It is exactly in the same way as we get from here to this form by the generator of this form, but approximated in the quantum optics version to no longer this integral, but the field operator evaluated at 0, right? So we still have a gauge transformation from the minimal coupling to this new dipolar Hamiltonian.
That's right. So there's a gauge fixing going on here, and the gauge fixing is usually ignored. People just say, oh, let's just consider the D times C Hamiltonian.
Yeah. So I know there's that gauge fixing thing that might happen once you forgot that this is not the most general one. I'm just asking whether 16 was naturally going to be different from 14, not this one.
Well,
so to this one.
Yeah.
So the difference in between is the evaluation of the electric field operator.
Yeah, because what it looks to me is that naively, right? If I change coordinates, that only shifts the x coordinates by some constant, right? Will my predictions change? That's the question, right? Because now the electric field operator the wave function is going to evaluate different wave functions, right? Well, this one will fix to 0 even if I change coordinates, right? So I don't know.
No, this 0, if you want, is the coordinates of the center of the atom. The point.
Yeah, but it's not a 0 operator. That's the point, right?
It's not a number 0. It's let's call it a 0 vector and call that the position of the center of the atom. So maybe it should be better called R0, right? Rather than a 0, call it R0, and that's in any frame the position of the center of the atom.
Exactly.
Yeah, but that means that if I do a unitary transformation that only shifts r by r plus some constant, right? Then the center one will not be fixed, right? The center for this one will be fixed. Is that wrong?
So R0 would be the coordinates of the center in whatever translated frame you're considering. So
what is assumed here is that we are in the center of mass of the atom,
That's
or
right.
basically where the proton is at the zero vector.
Okay. Maybe I'm just asking something really stupid, but never mind. So, but yeah, the original one, my question was already answered. Thanks.
So maybe for continue, one thing that you will see sometimes in the literature is that they write P times A equals R times C. And that, when you see that, you should be thinking, no, that's not okay. That's not correct. That's kind of the thing I want to introduce them. I don't want the talk to give the impression, even though what Richard is saying is all correct, from 15 to 16, things have happened.
Yeah.
No,
So
I do get the fact that in principle, you shouldn't be cutting off like at the level of the Hamiltonian. So, but anyway.
Yeah, again,
Sorry.
So it's a gauge transformation that brings us here, and in general, we have like the subleading correction in between these both models.
Yeah.
And if we work with this further, then we can derive the usual quantum optical models. And so usually we assume we have now a qubit as our atomic system, so just two levels instead of all the level system. We also perform a single mode approximation, so that means we have to be in some kind of cavity usually, and also very common is the rotating wave approximation. And I'm not going to derive that here in detail. I just want to say that from here, with these approximation, we can get to the Jaynes-Cummings model, which is basically this intuitive number conserving interaction of a photon being absorbed by the atom and the atom being excited, or the reverse process. And this you can also generalize to the Dickey model, where you have n two-level system interacting with a single mode of an electric field in the cavity. And so what we see now, this is of central importance in quantum optics, and there's a slight difference between if coming from your approximation you do in the beginning or you don't, where you assume that the electron is essentially at the center of mass or not. And if we want to work now again with the first term, where the electric field is evaluated at the electronic position, let's go now to the position representation explicitly. So we expand in the insert unity in the position basis associated with the R cats, and we expand also in the atomic energies of the free Hamiltonian of the atom, and find then in the interaction picture that we can define the dipole operator. And here it becomes really clear what I meant earlier, that the localization is given by the Bohr radius, because now through this procedure we get automatically the wave functions, which are localized approximately depending on the energy level with the Bohr radius. Now from the interaction picture, we also get the phase associated with the energy difference between this transition of the states we're considering, and we get the ladder operators between atomic states. Right. Okay. So let's recap of what we saw here. So we saw that we assumed a classical proton, and but by that effect also essentially a classical center of mass. In principle, you can do now consider classical trajectories of an atom moving on an arbitrarily relativistic trajectory. But it also means that we neglect center of mass dynamics, and that we will not be able to account for all of atomic dynamics that come from considering all of the quantum degrees of freedom associated with the proton or with the center of mass. And so now that we saw that, let's take a step back and look at the multipolar Hamiltonian if we consider a two-particle system of the atom. Similar to what we did last week, if we consider an electron and a proton that interact minimally with the electromagnetic field, and again, we will not consider spin here, then we can write the relativistic classical Lagrangian, where this is the relativistic expression for the particle content. We have here the field content and a minimal interaction between the charge currents and the charge densities and the fields. Now, A tot and U tot means that we are considering here explicitly the fields are generated by the charges as well. In particular, this will be also important to sub-relativistic correction order. So,
Richard.
yeah.
I'm gonna ask something really stupid, okay? So maybe you will just confirm whether I'm right, okay? So the first term, right, is just the free center of mass dynamics of each particle.
So this is not yet in the center of mass coordinates or variables. This is electron and proton position here still.
Yeah, but it's the relativistic particle trajectory kind of stuff, right?
Mm-hmm.
Okay, the second term is the current coupled to some A mu. Is that right?
Yeah, so it's the usual minimal coupling.
But there is no DT. Oh, I guess you factor out the DT as a Lagrangian density, I guess, right?
Mm-hmm.
And then the third one is just the electromagnetic invariant, -1/4 F mu, right?
Yeah, so that's the free light matter term.
Right. Okay, cool. Thanks.
Mm-hmm. Okay.
So the DT will appear when you write an action, right? And integrate this Lagrangian.
No, yeah, because I'm not used to writing these things, so I just want to be sure that I'm seeing the right thing. But yeah, right. Cool, thanks.
Okay, so again, we are not going to work with the relativistic description of the particles, and as we discussed last time, why don't we do this? So there's no relativistic quantum theory where we have just a fixed number of particles. So what we're considering here now is a non-relativistic or sub-non-relativistic description of our atom with a fixed number of particles. Here it is 2. Usually, or the correct way would be then the field theoretic one, where we consider our particles to be excitation of the Klein-Gordon or Dirac field, depending if we want to consider spin or not. And this will be the topic of next week. Okay, so what we're going to do is an expansion in the field velocities and the particle velocities, and we go to sub-leading corrections, so r dot squared. As last time, we're going to do a Legendre transformation. That means we're going to go to the minimal coupling Hamiltonian and do then a field quantization. So we're going to quantize the degrees of freedom associated with the electron, the proton, and all the field. And so then, without choosing a gauge here, we have the 2-particle minimal coupling Hamiltonian. So that's the usual term with a Coulomb interaction between the 2 particles. And to subleading order, we have what is known as the Darwin term, right? So the Darwin Hamiltonian can be written in this form. The important point about it, and I will discuss this later on once we have the correct operators to describe it with, that this Hamiltonian is important for the internal and center of mass degrees of freedom and allows for a dynamical description of mass and energy of the atom itself. Okay, but this we will.
Sorry, I'm going to ask another stupid question. So go back to the previous slide.
Mm-hmm.
So that expansion to order velocity over c is the velocity over c squared, right?
Mm-hmm.
So how should I make sense of this? I know I should know this, but it's like R is a quantized operator, right? So it's more like a virtual velocity thing that you demand, is it? Or
so the expansion that we're doing happens before we quantize, and then we do the Legendre transformation, and then we quantize. So
okay, I see.
At the
Lagrangian
picture, we do the expansion, right?
Right. Okay, cool.
Okay. So let's discuss in detail what we're going to do here. So first of all, since we, as I said, do a non-relativistic description of an atom, we have to do a non-relativistic approximation of the atom and the motion of it. We have to then do a change of coordinates in terms of center of mass and relative operators. And this will allow us in this new form to have a very nice multipolar expansion of the field, which gives us a new Hamiltonian. And from then we can do a canonical transformation to a new Hamiltonian representation in terms via the means of what is known as a PZW transformation. And then we are in the position to understand now this multipolar Hamiltonian, in particular in terms of expanding it in terms of hydrogenic wave functions. And once we understand all the relevant physical terms in this Hamiltonian, we can discuss a bit more what happens if we include relativistic corrections, because again, this is a non-relativistic approximation. So we do to this leading order, we just have the usual minimal coupling Hamiltonian. And let's talk about gauge a little bit more. So as Eduardo said earlier, if we gauge transform, we also need to gauge transform the wave functions. But since we are considering a two-particle scenario here, there is just no gauge transformation such that our wave function in this new gauge are the typical hydrogenic textbook ones. And so what is more is that we have strong qualitative differences in the shape of the wave function for different gauges. And besides from gauge, there's also the problem of the A² term, so which is usually neglected, but you cannot always do that, especially if you're in certain cavity scenarios or if you consider non-dilute media. And so that is some of the reasons why it's very beneficial not to work with the minimal coupling Hamiltonian. And again, we do go to a multipolar Hamiltonian as before, but now in a fully quantum case. And what we want to find is this multipolar Hamiltonian, again, in multiples of E and B, in terms of the usual simple hydrogenic wave functions, and in the end, also the microscopic atomic properties. And so, to that purpose, again, we start with defining new operators in terms of the center of mass and internal coordinates or relative coordinates associated with the total mass of the atom and the reduced mass mu of the atom. We can also then define accordingly the total momentum of the center of mass and the momentum of the relative motion, and it's just as in classical mechanics. Nothing new here. The important point is that amongst these two sets of operators, our usual canonical commutation relations hold, and that is something very important for us now. And from here we see what it means that we have a non-relativistic approximation. So the relative internal momentum, which is essentially the electric momentum, has to be bounded, but this is usually given anyway in a hydrogenic atom, that the electron is rather non-relativistic, and so this is not a restriction. The real restriction is that the total center of mass momentum has to be bounded, and therefore we can only consider overlap with eigenstates of the total center of mass, which are very non-relativistic. So now in this new, with these new operators, we can now choose also a gauge before we choose a gauge, the Coulomb gauge. This will eliminate the scalar potential. We can write this now in this new form of operators. And importantly, we will not neglect here the A² term. So once we've done this, we can do our expansion. In general, you have a multipolar expansion, but for our purposes, as in the first talk and the first part of this talk, we do a dipole expansion. So we go to position representation associated with the cats of center of mass and internal degrees of freedom of the atom, and expand then the field operator around the center of mass, not just to leading order, but we have to go to subleading order. Because we're considering a dynamical center of mass, this is important, and this will be already a leading order interaction in this new multipolar representation of the Hamiltonian. Now, so this term here is suppressed by the Bohr radius and some maximum wavelength of the field. And again, so this can be either come from our physical process that we're considering. In the end, is upper bounded by the Compton wavelength, but usually one has to be below the Compton wavelength in order to have a valid Taylor expansion of the field operator. So again, what we want to find is the multipolar Hamiltonian in terms of hydrogenic wave function and the microscopic matter properties. So now that we have the Hamiltonian and these new operators, we want to look again at canonical transformation. And this will be not a gauge transformation, since we are not considering one particle, but two particles. So again, we have a generator for this canonical transformation given by lambda. And this gives us yields from the old Hamiltonian and the old state, a new Hamiltonian and a new state associated with the system. We can then just define our new state in terms of the old one via this canonical transformation. We plug it into the old Schrödinger equation for the old state and can write it in this form. So this has to be then equal to this expression with just the right-hand side of the old Schrödinger equation now expressed in the new state. By some rearranging, this allows us to define the new Hamiltonian. And so this was just a slightly different derivation of the canonically transformed Hamiltonian to what we saw last week, where we also found that the Hamiltonian is not unitarily equivalent to the new one, since we also have in general this time derivative of our generator. And this again will mean that in general, not every Hamiltonian is equal to an energy operator. And what we need now here is the Powers-Zienau-Wolley transformation, the PZW transformation that brings us from the minimal coupling Hamiltonian to this multipolar Hamiltonian. And in general, it has this form. So this looks a bit, so this is the generalization of what we saw in the effective case, where we just considered the electron to be quantum in the first part of this talk. We can now approximate it since we're just considering the dipole approximation. Of course, it's possible to do this full canonical transformation on the full multipolar Hamiltonian without doing the expansion in the field. And after this transformation, we do an expansion of the field. This is equivalent. What does this generator mean? So we can rewrite it in terms of proton and electron degrees of freedom. And from here, one can see this is just a special case of the line integral over the vector potential from the proton position to the electron position. And so what it means is now that we're connecting the proton and the electron on a straight line, the simplest possible case that we can consider. And again, this is just a generalization of the semi-classical scenario. So now after this transformation, what we have is this new Hamiltonian in terms of electric and magnetic field. And now we want to analyze all of these terms in more detail to understand what each of them means, since it seems to be more complicated than the minimal coupling, but of course it's exactly what we want. Again, we have two small parameters here, that is the coupling E and the spatial support given by the Bohr radius of the atom associated with the reduced mass mu. And now we want to order all of these terms according to these two small parameters. First of all, to highest order, that is quadratic in E and quadratic in the Bohr radius, we have the diamagnetic term, which essentially comes from the A square term in the minimal coupling Hamiltonian. And we have the self-energy that, similarly to the semi-classical case, is also from self-interaction. So we need to regularize this, otherwise it is UV divergent, and after regularization it corresponds to a lamp shift. And this term comes exactly from the canonical conjugation of the time derivative of the generator of our canonical transformation. And specifically, we can rewrite it exactly without approximation in this form, and this comes then from the commutator of the generator with its time derivative. So we will be able to neglect this for our purposes. Then to linear order an electric constant, we have the magnetic dipole, which comes about from the currents effectively associated with the electron that couple to the magnetic field. And we have an electric quadrupole term. We will also be able to neglect these two terms. And then to leading order, we have this dipole Hamiltonian, so linear in E and linear in A0. This is exactly in terms of the hydrogenic wave function and the usual dipole interaction, but some more. So what is more is that, of course, we have now the center of mass degrees of freedom. We have our internal degrees of the atom that yield the hydrogenic wave function solution. We have the dipole term that is evaluated at the center of mass coordinate, and we have the Röntgen term. So what one cannot do is just consider the semi-classical case that was essentially this and this term, and then say, okay, now I assume that we have center of mass degrees of freedom and just insert this term. Then of course we would not get this term, so one has to do it the right way. What is important now is also that the interaction localization is no longer given by the electronic wave function, but by the center of mass. And we can also show that this Hamiltonian, this interaction Hamiltonian, accounts for Doppler shift and atomic recoil. So let's rewrite it again. So now to leading order, we just have the free atomic part and the interaction between atom and field. Let's do something similar that we did in the beginning. We want to find now the position representation, but we do a mixed representation now. We want to find the position representation in terms of the internal degrees of freedom associated with the small r, and the momentum representation of the center of mass degrees of freedom associated with capital P. So first of all, you can show that the internal atomic degrees of freedom are clearly separated from the rest, where we have then the center of mass degrees of freedom and the field degrees of freedom. And from here, you already see that the center of mass naturally changes its momentum by absorption or emission of photon with a specific wave function. And usually you would just have in the semi-classical case just the this term that is associated with the usual dipole term, but now to the Röntgen term. Again, the Röntgen term is the currents that are associated with or generated by the center of mass motion coupling to the magnetic field. And this is 1 over mc dependence here. Now let's look exactly at what does it mean if you have in principle center of mass delocalization, and if we allow the Röntgen term to be part of our interaction. Particularly, we want to look at transition rate, and we allow now the center of mass delocalization is just saying that we have a center of mass momentum distribution of a Gaussian with some deviation sigma p. And we want to see how is the spontaneous emission rate from the 2pz state to the 1s state, where we have transition frequency between these two energy states of capital omega. Now the usual term is again this prefactor here. This is the standard textbook one. And the correction terms are now the following. So we have first linear in capital omega. That is if we have any non-degenerate state, then we have a correction term through the transition. And we also have something that's purely from the center of mass delocalization that is quadratic in the uncertainty. And again, an eigenstate of the center of mass momentum is unphysical. And so in general, you will always have this correction term here. Now let's talk a little bit more about this Röntgen term, since we clearly did not have it in the usual form of our models. And it only came now through this quantum center of mass. So if we have a quantum center of mass, of course, we can never neglect this term. The best we can hope for is we have perhaps a quantum reference frame or so where we have on average the center of mass momentum to be 0. But through this entangling interaction between all field degrees of freedom, you always will have some kind of spread in the center of mass momentum, and you will never really be able to neglect this Röntgen term. What we did in the very first part of this talk was this box here. So we had a classical center of mass and no atomic motion. And of course, there was no Röntgen term since we had no atomic center of mass motion. If we have, on the other hand, center of mass motion of the atom, then you will in principle always have again this Röntgen term, which just comes about in this case from a classical analog to the Röntgen term, unless of course you have some kind of further approximation to always neglect this term. So the important point now is here that in the quantum case, you always have the Röntgen term. And also in the classical case, whenever you consider an atom to be in motion. So let's talk now about the relativistic correction. So what we saw earlier, that the subleading relativistic correction that comes from the expansion in the particle velocities in the Lagrangian picture yields then, after Legendre transformation in the Hamiltonian picture, the Darwin Hamiltonian. And importantly, it changes the internal dynamics it changes the center of mass dynamics of the atom. First of all, it no longer allows you to have a very simple wave function solution for your atom. Is something more complicated, since we have much more complicated coupling between all degrees of freedom. But the important point of this relativistic correction is that one can account now for dynamical mass of the atom. In principle, if you were to study forces acting on the atom, you would find that you will have vacuum friction forces acting on the atom. And so in the leading order non-relativistic approximation. But if you now consider the subleading correction term coming from the Darwin Hamiltonian, you will find that this is nothing else than just changes in the binding energy of the atom. And so there's apparent friction forces that come from the non-relativistic calculation are no longer there. And therefore, in the end, if you're interested in forces acting on the atom, it's important to consider corrections, even if it's just a subleading order. Okay, so let me conclude. What we saw was that we had two ways to derive the multipolar Hamiltonian. The first, what I call the effective version, was just the usual models that we very often use, where we just have one electron coupling to the electric field operator, where the proton is just a classical degree of freedom that generates a Coulomb potential for the electron to be in. And the other one was the fully quantum version, where all degrees of freedom are quantum. So we saw now that by the first method that we neglect the dynamics that is associated with its center of mass. And this can be of importance already to leading order. And we saw this throughout the derivation of the quantum Hamiltonian, that we have not just the center of mass dynamics through delocalization, but we also have this Röntgen term that coupled all the internal and external field atomic degrees of freedom and the field degrees of freedom. We also saw that in principle, you can only in very few scenarios neglect this term. So what we're going to do next week is we want to find a covariant formulation of quantum electrodynamics. So we want to consider relativistic formulations in principle and find then that we can have the limit of this formulation allows it to go back to what we saw in this week and the previous week. And in this way, we have to discuss a couple of things. So first of all, in order to have this covariant formulation, we need to introduce more degrees of freedom than we did in the simple Coulomb gauge quantization of electromagnetism, QD. And therefore, through this more degrees of freedom, we will have to introduce constraints. And these will, in the end, allow us to find the physical states of an enlarged Hilbert space. So in order to have this suitable description of a relativistic and covariant form, we need to enlarge our Hilbert space, and then we can find through a little bit more steps the physical states. But this we will see in the next week. And with that, I want to conclude and invite you for more questions.
All right, thank you very much, Richard. Very good. Do we have questions? If you have questions, just unmute yourself and ask. We're few enough that we can do that. Well, if there aren't any more questions, then let's thank Richard. Thank you very much, Richard. Great seminar.
Thank you.
Okay, I'm going to stop the recording now.